Going live here. All right, let's go over. Hopefully, well, who got an answer I feel relatively confident in? Julia, anyone else? Emily, sort of, kind of. What'd you get, Julia?
I got 0.75 meters. That's what I got.
Good. Okay.
I'm seeing.
Can you explain how you got it?
Well, block A and block B are in a 1-to-3 ratio. So I assumed that the lengths would be in a 1-to-3 ratio, and then I put those into the formula and it balanced out.
Good. So you used torque to check your answer, but you found it just through the proportional argument. That's great.
Mm-hmm.
Nice job. I'm going to show you another way to do it. Hopefully that made sense. You heard what you said. That's a great approach. Here's a more algebraic approach, I'd call it. So this guy is 5 kilograms and this guy is 15. So I'd say, well, in order for this to work out, the torque from block A must be equal to the torque from block B. Okay, so this whole rod is 1 meter long. So let's call this distance X. If I decide to call that X, then what would that one be called? 1 minus X, right? Because the whole thing's 1 meter. And so if you do that, you can write, well, okay, so this guy's torque is, the force is 5G. This force is 15G. So I can say, well, my torque is force times radial distance from the pivot, center of rotation. So I can go 5G force multiplied by the distance is equal to the force, 15G, times that distance. And then from here, it's a pretty basic algebra question. So, because the G's cancel right out. And so you have 5X equals, distribute the 15, 15 minus 15X, add that over. And you get X is 3/4. Like Julia said, well, just look at the ratios involved, right? 3-to-1 ratio, so the distances have to be in a 3-to-1 ratio for it to balance out. So 3/4 and 1/4 of a meter are in a 3-to-1 ratio. So. Do you feel okay about that? Okay. I want to look at 6. And then I want to get to the sort of you got to do 6. Then I want to talk about what happens if you exert your force at an angle. And then I want to talk about Newton's law. So look at 6. It's a lot of wordies there. Wordies. There's a 4 meter long plank with a total mass of 50 kilograms and uniform density. Do we all know what uniform density means? Yeah. It's it could be a steel plank or a wooden plank. Just means that it's not the case that the left half is made of styrofoam and the right half is made of iron or something weird like that. The whole thing's the same density. Anyway, it's connected to a fixed structure by a hinge on the left. You can see that. And the plank can rotate about that hinge. So there's 4 possible locations where you can stand and hold up the plank. So just using some common sense here, where do you think is going to make it easiest for you to stand and hold up the plank?
Farthest away.
The farthest away? Okay. Anyone disagree?
Right in the middle.
Could be right in the middle. Good means. Okay, now so what the question's asking, find the amount of force you would need to supply at each location in order to hold the plank in its static equilibrium, in its horizontal position. And so the hint is, think about the rod's center of mass. Here's the rod. Sorry, the little dashed lines aren't, they're a little wonky, but the question says, well, you got position This is 1 meter. Then you got 2 meters. You could go 3 meters, or you could stand way out here, at the end of the rod. So the hint is, think about the rod's center of mass. Where's the rod's center of mass? Right here. So let's figure out how much torque does the rod's own mass exert on the system, right? So what the trick is, for you calculus people, what you technically do is you actually draw a whole, well, you don't draw them, but you imagine a whole bunch of tiny little vectors. Each little piece of mass pulls down, and then you do an integral over the whole rod to figure this out. But anyway, the spoiler alert, the result of that ends up being, hey, it's actually the same as just a single force exerted at the center of mass. So, okay, so I'd say wherever you're going to stand, right? Let's say this is you. You can analyze this one first. Here's you. Here's you. You're going to exert a force upward, and then the rod has a force exerted downward, right? So what you do is you'd say the force, the torque exerted by the rod's mass, so I might call it the torque caused by the rod, has to be equal to the torque exerted by you. Make sense? So what's the torque exerted by the rod? So let's do in this case, you'd say, well, how much mass are we imagining is concentrated there? 50 kilograms, so 50 G, 490 newtons of force, right? And since we are, well, see what happens. So this is the force multiplied by, what's the R value for this? 2 meters. And then your torque for this one would be the force that you're exerting multiplied by the radial distance of 4. Notice that G is not going to cancel out this time. What? Very funny. Very funny. So this is what, 490. So this is 980 divided by 4. So it's like 245. Is that right? Any calculators can help me out? I think that's right.
245.
Okay. Okay, so now interpret that number. How much, if you just balanced this board above your head with no hinge, how much force do you have to exert? It's 50 kilograms.
490.
490. So you could also, I mean, in this particular case, and you can kind of think, it's almost like you're standing here and your friend is standing here to lift the plank. So you're kind of just sharing the force equally. So
That's what I was going to ask you. So since it is on a hinge, is the center of mass, does it still have, like obviously it is here, but like in a real life application, is it still the middle or is it pushed in a little bit if it's being?
because of this mass,
Yeah.
oh, if you wanted the center of mass of this and the rod, then it's probably going to be somewhere like, I'm guessing like here, or I mean, if it's made of concrete, it's probably like here.
Okay.
But the thing is, I don't care about this guy's mass because I want to know how much torque is the rod exerting on the rod, basically. So I don't really need to care about that guy. It's a good question though. Okay, so then what's the answer for if you stand here? Calculation is very similar. It's
3 instead of 4.
yeah, same calculation, but a 3 instead of a 4. So what are you going to get there? How much?
326.7.
Yeah, go ahead and run the calculations. And you're going to find one that's maybe a little weird. You might find it like kind of strange. Give me a second to do that. Did we figure out which one's the weird one? It's not that weird. It's just you might be like, it might cause you to be like, is that really true? Which one is it? The 1 meter one. Because how much force are you exerting here? Here? No, not here. Because if you stand here, look at the calculation.
Oh,
You have to go, the rod is exerting 980 newtons at a distance of 2, and you're exerting F newtons at a distance of 1. So the force you have to exert from that position is, what is that, 1960? So why is that a little strange, you know? You're like, well, the thing only weighs 980 newtons. Do you see how that's a little weird?
how'd you get the 980?
But how did they get those? How did they get that?
Because, did I mess up? Because the rod is 50 kilograms, right? So he,
50 V times 2. F is 90.
oh, you're right, you're totally right, sorry. All right, the torque is 980, thank you. So yeah, I was using this number from before, sorry. So it's 490 newtons. This is why I should label my diagram, right? So it's 490. Is that cleared up? So so the point is you're exerting twice as much force as you would be if you were just picking up the plank, right? So why is that?
Because it is, you're not like pretty much the fulcrum because it's wanting to fall back. It's exerting torque on you, kind of.
You can maybe think of it that way. That's not how I'm thinking of it, but that might work. I was thinking of like, well, what's the hinge doing now? Like earlier, you were pushing, like when you were over here, you're pushing up, and what's the hinge doing effectively? It's pushing up the plank. You're both kind of pushing up on it because the plank wants to fall to earth, right? But when you're here, the hinge is actually pulling down, right? Because the thing, like you said, it wants to. When you're standing here, the plank wants to rotate clockwise around your hand. So the hinge actually has to hold it in place. Does that make sense?
Yeah.
So that's what's going on here is the hinge is actually pulling down. So in order to prevent the thing from hitting the earth, you have to push up twice as strong or more strong. The closer you get, it's actually kind of asymptotic here. As you approach this, your force actually kind of approaches infinity if you want to think about it mathematically, but do we feel okay? Okay. I think 9, you shouldn't have any trouble with the spring ones. You won't have any trouble with those, I don't think. Just remember for a spring, what's the force equation for a spring? No, that's spring energy. F equals kx,
Okay, that makes sense.
where x is the displacement. Okay, so like when you look at when you do one of these problems, the force calculation is very simple. It's just, oh, did the spring stretch this much? Okay, just multiply that much by the spring constant. That'll tell you how much force the spring is exerting, and you'll have to multiply that force by the radial distance to get the torque. Fair enough? If you get stonked on them, then we can discuss it in class. But I feel pretty confident you guys can figure those out in number 9 without my help. I do need to go over 10, which is, I mean, it's necessary, but you might find it kind of silly because you might be thinking like, why would you pull a wrench at an angle like that? Doesn't really make a ton of sense, but there's times when you want to talk about, well, there's force exerted on a system, but not necessarily at a right angle to the radius. So how does that work? So anyway, let's just get into it. Here's the wrench, or here's the circle along which the handle of the wrench is going to rotate. Here's the wrench, and we're drawing a really good picture for you guys. There you go. Okay, there you go. There's the wrench. So it says you've got a wrench that has a length of 0.35 meters. Okay? And you're going to apply a 400 Newton force. What?
Never mind. I thought you said 3.5 meters.
Maybe I did, sorry. For 0.35.
That is a big ass wrench.
That would be big, actually. It's 0.35 meters, so yeah, I spelled this one. So anyway, the idea is actually very simple. It's just, you'd say, well, according to what we looked at the other day, right, if this is R and this is the force, then the torque is the force times the R. So, well, in this case, what do you think I'm going to do if I know this angle? I'm going to use some that horrible black magic called trigonometry. Okay, so which component do you think I want? Do you think I want this component or this component? I want this component. This component's not irrelevant. I mean, this might tell you, like, is the wrench going to stay on the bolt, right? Is the wrench going to pop off the bolt? But anyway, so we want this one, though, in terms of wanting to know what's that perpendicular component, or we'd call it really the tangential component of the force. And so who remembers how to get this if I know the hypotenuse and the angle?
It's
Sine.
Yes, it's 400.
50-50 chance there, sorry.
50-50. Hopefully it's not 50-50. It should be 100%. That's okay. 400 times the sine
Or
of 53.
33%. No, I knew it wasn't tangent. Tangent is when you're looking for the hypotenuse. Oh, that's
319.
No, it's not. Tangent is the ratio between the opposite and the adjacent.
yeah, right. It gives you the hypotenuse. Right? No.
Tangent would be like, if you had, okay, so say this was 27 degrees and you knew that this was like 10 feet. You'd go, and you wanted to know this. You go, oh, the tangent of 27 is 10 over x. Then you'd solve for x. That's the,
Yeah. Okay.
you can use sine to find it. So suppose you wanted to know the hypotenuse, you would then use sine. You go sine of 27 is equal to 10 over the hypotenuse. And so the hypotenuse would be 10 divided by the sine of 27.
It was a 33% chance. I stand corrected.
What does this come out to be? 319? Oh, let's go with 0.5. Okay, 319.5 newtons. Great. So you can see a lot of that 400 newtons is actually translated into the effective force that's actually causing the torque. So obviously, the skinnier that angle is, the less you're going to get here, right? So the answer to this one would just be the torque. So let's maybe modify this formula. It's actually let's call it like the perpendicular force. It's how much force is actually perpendicular to the radius, or we could say tangential. Tangential to the circle, multiplied by r. As a point, it's just a little trivia for you. Those of you that end up doing more math and stuff, if you want to get really technical, it's actually the truth here is if you ever look this up in like a college textbook, you'll actually see something more like this, where this is a special operator called a cross product, because you have to treat the r like a vector and the force like a vector. Because if you want to start doing this in 3 dimensions, it gets complicated unless you can treat them like vectors, and so just something to look forward to for some of you. Okay, so anyway, so what you really have here is you have 400 times the sine of your angle multiplied by the radial distance, which was 0.35. And so what does that all come out to be? Okay, that sounds right to me. Units of torque here, Newton meters. There you go, that's it. Okay, I'm not going to do 11 with you unless you all get stomped on it, but 11's asking you to get the exact answer. It's a little bit different. They're giving you the torque and they're giving you the wrench length and the angle. So it says don't use a calculator, get the exact answer. So what quantity are you going to have to know for this question then, given how we did this one? The sine of 60. What's the sine of 60? What's the exact value of the sine of 60? What?
Root 3?
Root 3 over 2.
Okay.
Half of root 3. Root 3 over 2.
I think I'm reading it somewhere.
Root 3 is a thing though, Caleb. You know, I'll give you $1. You can tell me which famous trig thingy is exactly root 3.
No, root 2 is 45, 90. Root 3 has to be the short side of a 30, 60, 90.
You're in the ballpark. You gotta take a guess. For the dot, it's big money.
Yeah. The long side of a 30, 60, 90?
No. Well, the long side of a 30, 60, 90 can be any number, but it's the tangent of 60.
Oh. I should have put 2 and 2 together.
Because if you have, well, the one you did in geometry class was there's your 30, 60, 90, that being the 60, so the tangent is not divided by that.
Oh, okay.
In algebra 2 and pre-calc, you actually divide all these by 2 because you want to put it on the unit circle. So this becomes 1, this becomes half of that, this becomes half of that. So, same ratio though. Unit circle, our favorite, right, Julia? Okay.
No, wait,
What, Julia? What's wrong?
you like unit circles.
We're not doing that.
Oh, okay, that's good.
Okay, number 12 is going to hopefully, this will all make sense. So this is going to get us towards a really bigly result in rotational mechanics. Okay, Newton's law, basically Newton's what's Newton's second law? What's Newton's second law that we use all the time? F net equals ma.
So
So
every reaction is every reaction.
that's Newton's third law. Newton's first law is basically setting out like, well, a thing that's moving is going to tend to keep moving unless a force acts on it. Okay? That kind of dispels the myth of the impetus of like, oh, what's causing this thing to move? Oh, some kind of magic dust. No. If things move, if they're moving, they're going to keep moving. If they're still, they're going to stay still, unless you actually have enough force. And then the second law is, well, what's a force? A force is equal to mass times acceleration. And then the third law is talking about, well, what happens when I exert a force on something else? It exerts a force back. So that's his three laws.
Didn't you want to live in a time when these were bills and not laws yet?
No.
That was actually pretty good. I gotta give.
No.
I give that
You're lowering your
7
standards.
big blue moons out of 10. That's a 7 out of 10.
No. That was rough.
The bar has
What'd you
been dropped.
You said,
All right,
Can you imagine living
Lindsay, can you put your laptop away? You're killing me.
I'll have to tell that one to Ozzy.
come home with that one.
Okay. All right. So there's a ball of mass m attached to a motor by a massless rigid rod. If you're wondering why are you including all those weird words, you can make these questions extremely complex by saying, "Oh, this rod has a certain flexibility to it." That complicates things. I mean, way past anything we'll ever cover. Or even, what if you give the rod some mass? That would be also complicating things. I think, Colin, weren't you the one talking to me about that truck you were looking at where they put bigger wheels on it than it was supposed to have?
Well, yeah, it can still work, but normally if you put like the wheels on something, you want to re-gear the differential, so you get the power juice.
Yeah, I was just thinking like, if you have a car and the car is designed to like exert a certain amount of torque on the wheels to spin them, and then you put much bigger wheels with more mass, then that could be a problem potentially because it's designed to exert a certain amount of torque, but now the wheels, if you increase this M, it needs more torque in order to go fast and accelerate. Anyway, so derive the relationship between the torque exerted in the system and the system's resulting angular acceleration. So what are we looking for here? Let's start with what we know. We might say something like, I know that the force, right, because the motor exerts forces on the rod, which then exert a force on the mass that push it, right, that accelerate it.
Yeah.
And that force is equal to the ball's mass times its acceleration. Do we all feel okay about that?
Mm-hmm.
Okay, now, who knows, maybe this one. What am I going to do to both sides of this equation? Because I want to get torque involved. It's one simple step. And the idea is I want my equation to have this term in it. I want that guy to live in my equation. How do I get him in there? Yes, very good. Multiply both sides by r. So I'm going to go F times r is equal to m times a times r.
I was gonna say
For any
divided.
Spanish fans, what's up?
I was gonna say divided by R. Would that get you anything just out of curiosity, or would it just ruin it?
Not immediately, because I know that torque is equal to force times r. So see what we just achieved is like, well, great. Now I can just call this left side tau. You can call the left side the torque. Does that make sense? And now, does anyone see? Huh?
See.
Is that what Mar is? I thought Mar was river. What's river? Rio. Oh, Rio. Right.
Mars.
Good one.
Oh.
It's just-
Quality over quantity. See, Caleb? What else am I going to do? Because I want to relate this to angular acceleration. I don't want this thing to have like a. I want it to have alpha. So what am I going to do? Anyone?
Oh, divided by time.
Divided by what? Divided by.
What can I replace the a with?
Divided by the radius.
No.
Caleb.
A equals alpha r.
Oh. I was going from alpha to beta.
Remember, guys, arc length is angle times radius, velocity is omega times radius, and acceleration is alpha times radius. It's all one big happy family of telling you what a radian is.
I was going.
Okay, rearrange this, and I get this formula. I get m times r, so mr squared times alpha. Okay? Do we have any questions?
No.
Okay, part B says let's define a quantity I, which we'll call the system's moment of rotational inertia. This is a real thing. This is not something I'm making up. So that the relationship above can be written in a form analogous to Newton's second law. So does it, I mean, it's axia. Do you see it? Who's I?
T.
Exactly, Aiden got it. That thing. This right here, we're going to call that the I value for the system. Okay? Kind of a weird quantity, right? It's the mass multiplied by the square. Sorry I used a lowercase r, but you get the same idea. I guess. I was just testing you. No one told me. So now what does that do? So that says we are going to define this quantity. If that weirds you out, we actually do this all the time, but it might not be super obvious. We'll do it with force. Like, what's a Newton? A Newton is when you multiply the mass, the kilograms of something, by how many meters per second squared it's accelerating and what generated that movement. So even mass, if you think about it, mass is kind of a weird thing. It's this weird quantity that tells you how many protons and neutrons, how much matter is in a thing, right? It's very intuitive, and it kind of relates to how heavy is it. So how hard? Anyway, same thing here. So the I value is mr squared. So now what does this formula read? It reads torque equals I alpha. Now hopefully you see how that is really, really similar to this.
Yeah.
So what's the rotational analog of acceleration? Angular acceleration. What's the rotational analog of force? Torque. What's the rotational analog of mass? I, rotational inertia. So while mass tells you like how hard is it to push something, right? Pushing 100 kilogram block takes much more effort than to push a 2 kilogram block. Well, that's what I does. It tells you how hard is it to torque something, to twist it. How resistant is it to changes in its rotation? We feel okay?
Yeah.
And as you can see, there's something really interesting here, which is like, what happens if you double the mass? Doubling the mass doubles the inertia, but doubling the radius actually quadruples the inertia. So that's worth noting. Okay. C says, if the system is initially at rest, what will be the system's final the system's initially at rest, and then the motor exerts a constant torque tau on the system over a time period t. What will be the system's final angular speed? What will be its final linear speed? What will we do? Yeah, thinky winky. Let's thinky winky. If you can think of the right equation to write, the rest of the question becomes extremely simple. And the hint here would be, well, what are we trying to get? What quantity are we trying to? What? Omega.
Yeah.
It says what is the final angular speed? So do I have a formula for angular speed? Yeah. The final angular speed of a system would be its initial angular speed plus alpha times time, right? Now in the problem statement, they're talking about t, right? And then they're talking about, well, I exerted a torque of tau on the system. So the letters I got to involve are tau. So there's two ways to write this answer that I think are both debatable. What's omega naught? 0. What's alpha? What, Kate? Very good. Alpha is just tau divided by I. Okay. So my final thing here is it's a weird expression because every symbol looks the same. Tau, uppercase I, and lowercase t, I think all have very similar looking things. Now, of course, you might argue, well, wait, you can't just throw I in there. You made up I. You should put the question. You should put the answer in terms of the original variables given, which is a fair argument. So you might also say, well, maybe it makes more sense to write this as tau over, now what's I? R squared, like that. Does that make sense?
Yeah.
And then how about the final linear velocity?
Oh, I know.
Multiply by,
Yeah, use this idea. V equals omega times R. So what's going to happen when you multiply your omega, this thing, by R?
Or cubed. Oh,
No, you have an R on top, and you have two R's on bottom. So you have tau. I'm going to move the T on top. Just feeling it, Tau times T over the mass times R. It's kind of a nice little formula, isn't it? Maybe, maybe not. All right, we're pretty much out of time. So the last one, there's one little step you got to take to do the last one. It says, same setup, but we're trying to get to a frequency of F. So remember that F, frequency, the frequency is related to the omega by that. Right? We've already done the math on how to kind of talk about, well, what's the omega? And then you solve that for t. Because it says how long will it take for this to happen? All right. Thanks for the million bits.